This is the week 8 lecture. We are still on the shear strength. To side by side. Yesterday, we have to do week 9. I think we discussed all this yesterday. Okay. Consolidation. Now we have to want to consolidation. Okay. So we can go over the slides first. Talked about uh, shear strength with these tests. Now we're going to talk about consolidation. Basically, consolidation is a process. It is a process that the soil is going through all the time. And in all the time, I mean not if it is completed. As in, let me say that I have some um, soil here, and that soil gets deposited in layers. Let's say that I have a clay or fine grained layer below my land. This is a plot of land that I have, and I wish to construct a building over here, uh, multi-story building. It not need not be multi-story. Just an example. Anything I want to construct over here. So there will be some loads that will be um, applied on the ground. So the top portion may be good, well graded C5 soil that I could feel that the ground is quite solid. But I would not know that there is a weaker layer at the bottom. As the stresses from my construction, whatever I have constructed here, let's keep it two-dimensional. I've constructed something here. So the stresses will follow 1:2 pattern, what we studied in stresses in soil, and whatever load I put here, at the center of the soil layer, whatever load there is. What this will cause is it will cause this clay compress, this clay layer to compress. So I will see settlement just below. I will see settlement just below my foundation. Okay. So how much settlement there is going to be can help me determine the factor of safety for construction of this foundation. And so basically, when you are putting in a load from the top and overburden over this layer, what is happening? It is effectively getting consolidated. So it was kind of at an equilibrium. It was at an equilibrium. It would not settle on its. The particle stresses, they were rearranged in a way that everything was in equilibrium. Now that I have increased the loading, the this soil will experience load that it had not experienced earlier, and under this load it will start compressing, because soil is compressible. So basically, when you have coarse grained soils and you have fine grained soils, coarse grained soils, because they are freely draining, they show immediate settlement. By the time you have completed the construction, all the settlement that can happen in a coarse grained soil, it is complete. Fine grained soils, because they have very low permeability, and because this settlement is happening by virtue of escape of water from the pores of this layer. So water needs to flow out, because if we assume that soil is a continuum, and under gravity there will be some water always, there is water inside this layer. If I want to compress it, I need to reduce the pore volume, because we assume that the particles are incompressible. And if I want to reduce the pore volume, if the pores are already filled with water, we assume that water is also incompressible. So where will this water go? What will happen to the concept of conservation of mass? So this water will flow out of these pores. And because the permeability is very low, it takes some time for the water to flow out, and that is why this becomes a time dependent process. It takes some time uh, for this consolidation to take place. The total consolidation or total settlement that will take place in a layer depends on the structure of the depends on the soil type, but uh, the porosity the it may take, depending on volume of voids, the volume of voids will control, or the porosity will control how much settlement the soil can actually see. But the time it will take to reach this settlement will depend on different things. That is what we study in consolidation, basically. So until now, whatever we have studied, we did not touch the topic of time dependent. So consolidation is it is very important that consolidation is time dependent. Until now, basically, when we are dealing with any kind of problem, you can either have, we assume the soil to be isotropic, homogeneous, and all of these things. So, but in real life, you may have a ground that has a spatial, uh, it may, the soil here will not be exactly same as the soil here. And then in height wise also you will see some variation in the soil properties. So that is something that is called the um, that is the temporal and I my mind is slipping. I can't remember the term, but spatial variability. So spatial variability of a property. This is what we study when we are making those um, flow nets. So in the flow net, we make this kind of thing, isn't it? So on this flow net, the velocity of flow. Yes, please.
What is FlowNet?
Have you studied the have you studied the seepage and permeability chapter?
Yes, ma'am.
So in seepage and permeability chapter, did you come across the concept of flow net?
Ma'am, I'm forgetting. I have not listened this term.
Basically, when we are talking about seepage and permeability, not necessarily permeability, but let's talk about seepage. Seepage is flow of water
What one
to,
is the Laplace equation?
yes, please.
Laplace equation.
I could not hear you.
I'm talking about the Laplace equation. There we have
In the lab, uh, which I could not hear you. Can you write it in the message, please?
ma'am in the Laplace equation.
Yeah,
You would have
Laplace equation. Exactly, exactly. Have you done this Laplace equation?
yes, ma'am.
So in so basically when we are one second, when we are talking about flow nets, we are talking about the spatial variability. Why is it so? Because, for example, you have a sheet pile here, and the water behind the sheet pile is at this height, and in front of it, it is at a lower height. You can see that there is a head difference. This head difference will cause the water to flow because soil is not impermeable. This will cause the water will have a tendency to flow from this side to this side such that this becomes equal, isn't it? It's like if you um, connect two buckets and one of the buckets has a higher water level, what will happen? The water will flow from the higher bucket to the lower until both of the levels are same. That is the equilibrium that will be maintained. So the water will start flowing like this. So these will be the streamlines, isn't it? And then you also have the equipotential lines. This is the solution of the, like, we solve this using the Laplace equation, but this comes as a result of us trying to uh, taking into consideration the x and the y, like the spatial variability in the soil. Okay, so the flow will not be same throughout. It's not like an open channel flow. that water will just gush. The flow will depend on the height, and basically it will follow this. So here we are talking about the spatial variability of the property. But in consolidation, we talk about the temporal variability. So basically, consolidation is a time dependent process. Why I mentioned temporal and spatial is because usually, if you have only spatial variability, you can solve your problem using ordinary differential equations. But when you have both, no, when you have spatial and uh, uh, temporal, if you have just one variation in one direction, you can solve it using ordinary differential equation. But when you have spatial and temporal or spatial variability, you have to solve using partial differential equations, and that is why you don't get an analytical solution like, for example, say tau is equal to c plus sigma tan phi. This is just an equation we use, but for consolidation and for this seepage problem, you will not have this kind of a solution. You will always have a family of solutions that are possible because you are solving the partial differential equation, because they are the variability is present in space as well as in time, or space or time. Okay, so even if you only had time dependency, no space dependency, you can solve it using an ODE. So if you have if you have one dependent coordinate, one independent coordinate, then you can solve it using ordinary differential equation. Otherwise, you have to use partial differential equation. So consolidation introduction. Okay. So some of the properties of the soil are, so this is the test that we do. This is an odometer. What we do is, it's a ring type of setup. We uh, usually press this ring in the sample that we have or the field, and we trim it, and we get the sample inside this ring. Then we keep this ring in an outer water ring, because we want this uh, sample to be completely saturated. So why do we want it to be completely saturated in triaxial as well as in consolidation? Is because you know that air or any gas is very compressed. When I put, it's like a sponge. You put on a load, it will just compress. But if you fill that, you have to fill the pores with incompressible fluid in order to actually calculate the compressibility of the matrix. If you don't fill the voids, it will just, because the air is too compressed. And the assumption with our saturated sample is always that water is incompressible. So, what you do is you load it, and then with time you see how the settlement takes place, and then you load it for almost 7 days. Twe- At 24-hour interval, you will turn a load, for example, 120 kPa, and then you you monitor this settlement for 24 hours. Then after 24 hours, you again load, and then you again load, and then you again load it. Okay. So the yes, please. You have a question?
No, ma'am.
Okay. So by this test, what we want to do is we want to uh, calculate the stress versus void ratio relationship, and we want to calculate the uh, basically stress versus void ratio relationship we want to calculate. And what we do then, normally if you talk about soils, the relationship between void ratio and the stresses, see the EP relationship here. P here is mean uh, stress, which is equivalent to sigma 1 plus sigma 2 plus sigma 3 by 3. Because in a cylindrical sample which is axisymmetric, you have sigma 2 equals sigma 3. You will have P equals sigma 1 plus twice sigma 3 over 3. Okay. So the mean stress, if you plot your void ratio with mean stress, you will see that the more you, this is quite intuitive, that the more load you put over the soil, the lower void ratio it will show, isn't it? We know this is quite intuitive that a soil, same soil under a load of 50 kPa and 100 kPa will have a lower void ratio under 100 kPa than the 50 kPa. Why? Because compressibility will be more. Okay, yeah, the voids that are compressed will be more under a higher load. But the complete relationship is somewhat non-linear like this. It's not like a linear relationship that is going this way. And this relation, if you plot on a log scale, will actually give you a slanting line like this. Okay. So this is the relationship between void ratio and the mean stress. Uh, and if we talk about pre-consolidation, over-consolidated and normally consolidated soils, we mentioned yesterday, we when we were talking about NC and OC soils. OC soil is something that, for example, let me say that this is a soil sample. I have loaded it up till 100 kPa, and initially it was something like this. Then I loaded it and it got compressed. Now it looks like this. I have loaded it in 100 kPa. Okay. So if I now remove this load, the soil will come a little bit back to its original form, not to its original form, but a little कैसे सिखाऊं मैं? Let me try. So initially the soil was like this. Then I added a pressure because of which soil got compressed. Initially the soil was like this. Then I loaded it and then I unloaded it a bit. Okay. So initially the soil was like this. I loaded it with 100 kPa and it showed some settlement. Then I removed the load and now this is the final shape of the soil. Now if I load this again with 50 kPa, it will not show as much settlement. It will not show the settlement as um, eagerly as it did here because its compression already was like it may compress a little bit here, but if I load it greater than 100, then I will see greater compression. That is what happens between, if you see here, the E versus P graph. What happens is log P graph. If the soil is normally consolidated, if the soil has not seen this mean pressure in its history, it will compress like this. You see, there is a greater decrease in the void ratio with P. But if I unload it now, it will go back not to its original void ratio, but to a lower void ratio as compared to its present void ratio. And now when I load it again, it will show this only this decrease unless and until I'm loading it back to its original PC. Let me call this as its pre-consolidation pressure. Let me have a normally consolidated soil. Okay. PC1 is the pre-consolidation pressure. After I load this soil, it will show um, reduction in void ratio like this, steep reduction. Now I'm unloading the soil So it will regain some of its compression back. Not all of it, some of it. Now, the pre-consolidation pressure of the soil is PC2. Anything lower than PC2, when I load it with, the soil will be over consolidated, and the relation between EC and void ratio and P will be such that the void ratio is reducing by a smaller amount as compared to it would if this was normally consolidated. And as soon as this point has crossed, it will start moving like this again. This is the volume change characteristics typical to soils, that they remember the loading that they have been experienced in their past. The soil has a memory of its stress history, we say. So, so this is the uh, slope. And as I said, for normally consolidated, it will be steep. Then this is reloading, unloading, and reloading. So coefficient of volume compressibility can be is equal to volumetric change over the like how much volume is changing with change in P. Compressibility of the soil. So PC P naught is equal to MV Total settlement is MV, where MV is the coefficient of compressibility, coefficient of volume compressibility. dP is the change in the normal stress that we have given to the soil, and H is the initial height uh, of the soil. The curve C3. Consolidation. So this is the Terzaghis one-dimensional theory. As I was mentioning to you, that you have a partial differential equation. This is the spatial uh, description of your flow, in which you are having different permeability in X, Y, and Z direction. Let us say that the material is isotropic, and it does not have different permeabilities in all different directions. So this will be K, and you take this out, this will be K del square H by del X, del square H by del Y, del square H by del Z. And if we are talking about flow in only one direction, we are not talking about flow in three directions. If we say one dimensional flow, that is, let us say, just flow in a vertical direction, bottom, then we can ignore x and y coordinates, and we will have k del square h by del z square, and this will still be there. And you replace this using the concept of porosity, what you will end up with is your compressibility, is your consolidation equation, which is basically this Cv del 2u over del z square equals del u by del t. Basically, this is an equation of, you can say, this is a flow equation. We talk about uh, you might have, you might read in your books that this is similar to the heat equation. There also we are talking about the flow of heat energy, and the change in temperature because of the flow of heat. Here we are talking about the flow of water or dissipation of hydraulic head with time. And in heat equation, you have a thermal conductivity concept. So basically, the rate of dissipation of your water pressure or the flow of the water through the sample is a function of permeability of your material multiplied by the spatial variability that is given by your we continuity equation. We use continuity equation to derive this Poisson's. This is when we talk about uh, uh, Laplace equation. Laplace equation is basically that is used for flow in any kind of medium, in water, in soil, flow of heat, flow of anything in 2 dimensions or 3 dimensions. So you're coupling the flow equation with uh, the permeability, isn't it? So you get this kind of an equation, and then you have a solution to it like this. So this will not be just one solution, it will be a family of solutions at different time t. Excuse me. So basically, what will this solution give you is through the sample, through the sample, your pressure head at, let us say, T equals 0, you will have a pressure head, and then this, this, this actually T equals 0, this. So these are at different time stamps. Okay. The equation gives you the variation of the head in x and y coordinates. Here, in just one coordinate, the value of uh, your hydraulic head, how it changes with depth. This is the coordinate, and this is the value of h. Okay, the equation will tell you when you solve it at t equals to t1, for example, it will tell you at every point what will be the hydraulic head, so that you can know that what will be the flow direction basically. And this is more important when we are dealing with the, when we are kind of computing with finite elements or FEM or FDM. So this is not as important to know time stamp exact analysis in real life when things are happening in real life, in at maximum what you want to know is how much settlement this layer will show, and how much time it will take for this layer to show the settlement. In normal scenarios, these are the end results we want. But to be more be more complete, this when you are modeling uh, the behavior of soil, the consolidation equation can show you actually. Let me show you.
Ma'am, what do we need to know in the modeling of soil?
um, Please repeat.
Ma'am, what should be the
Yes.
parameters that we should know before modeling any soil?
Okay, the parameters that you should know. Uh, so the parameters for let us say, if you are so the parameters that we want to calculate are the slope of this log p, and e line is cc. Okay, this is the coefficient of consolidation. And when you uh, when you unload it, this slope is called cs, which is swelling coefficient of swelling or swelling index. If you plot this like this, then the slope gives you cc cs. Another way of going about is, if you have specific volume here, which is equal to 1 plus e, and you have log of p here, then this slope is called lambda, and this is called kappa. The relationship between them is just of this change in the log base. So these are the parameters that you want to know, because let's discuss. Okay, this is what I was talking about, that you will know the profile at different time periods, but the settlement you can calculate without drawing the profile. F AV is taken as dE by dP, which is the instantaneous slope of this line if there is no log here. Then you convert it into mv, which is a over 1 plus e. This is your specific volume. So you are dividing it by your initial specific volume. This is your coefficient of volume compressibility. This basically tells you about this tells you about the compressibility of the soil, uh, and the settlement is, if I'm not wrong, it used to be settlement is CC EY plus E naught log of delta C. Used to be this formula, this CC log the base 10 P naught plus delta P over P naught divided by 1 plus E naught used to be the settlement, the total settlement that will take place in the soil. And if you need to calculate the time, then you have to calculate it through the consolidation equation, where TV equals half of U square. U used to be the degree of consolidation.
Ma'am, do we have questions or
Okay,
no? Because in this
we can do some
portion
questions
where
like this.
time has asked,
We can have some questions like this. This is okay. Following are the results of a laboratory consolidation test on a soil specimen defined from the field. The dry mass of the specimen has been given, height of the specimen has been given, the GS has been given, area has been given. Make necessary calculations to draw the E versus log sigma graphs. Okay, let's do that.
ma'am, sigma dash is the effective stress.
Yeah, just this. Okay. So we have been given your sample has a height of 2.4 centimeter, then you have a diameter of 6.25 centimeter. So in your phase diagram, if this is your sample of height h, we take the height of solids method, in which this will be the height of solids and this will be the height of voids. You know the height of the sample, you need to calculate the height of the solids. Height of the solids means that if there were no voids, what would have been the height of the sample given that the area is same. Okay. Why we do this is because we assume that the solids are incompressible. So any settlement that will take place will take place only by change in the height of voids. So first we determine the height of solids. Height of solids is equal to, let's say, let's see, gamma solids is equivalent to your gamma of solids over gamma of what. So this is weight of solids divided by volume of solids. Okay. And weight of solids, we have been given dry mass of specimen. Volume of solids we can write as area of solids,
Area into height.
height of solids. So this will be weight of solids over GS gamma W. So height of solids will be weight of solids by AS GS gamma W. This will be 128 over area is 30.68 into 10. Actually ग्राम पर ले लेते हैं. इसको 8.75 in 1 gram per cc. Gamma W can be taken as 1 gram per cc. So we are taking in centimeters and grams. Let's calculate this. This will be 128 divided by 30.68 into 2.7, almost 1.5. Let me open an Excel sheet. So GS is 2.75. height at the beginning is 2.54. Then you have dry mass, let's call it weight of solids, 128 gram. And then you have an area, 3.68. So your height of solids will be um, weight of solids divided by area of solids. Yes. So 1.51 was the height of solids. So what will be the height of voids? It will be just subtraction. We just subtract this. So this is the volume of, basically if you multiply it by area, so it is the volume of the sample which is available for change. Okay. Uh, Now you write your void ratio as volume of voids over volume of solids. You can also write it as height of voids into area of voids over height of solids into area of solids, isn't it? Since we are taking area same, so your void ratio will be equivalent to height of voids over height of solids. So this is the height of solids method of calculating the void ratio in height of voids over height of solids. Okay, so make necessary calculations and draw E versus log sigma. So effective pressure has been given, and we can make the graph by simply but I have to take this, the log scale. Okay, so you see this graph for the void ratio. We can add a trend line. Starting from okay. So this kind of a graph you will see. So it's probably an over consolidated soil. Let's move on to the next question. Following the other laboratory consolidation tests, calculate the compression index and the ratio CS by CC. On the basis of the average E log sigma dot dash dot, calculate the void ratio at this. Okay, let's do this. We have been given the void ratio, we have been given the sigma. All we need to do is we need to plot this. Now what we can do is during this thing, let's calculate it like this 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 this. But we can't do that. We have to put it because this has to be then in log. Either you can do one more thing. You can take this as log 10 of sigma dash. Yes,
Ma'am, the left
yes,
side graph is the end result.
yeah, yeah. That is why I did not draw the graph because I have already shown it here.
Okay, ma'am.
Okay, that
Yes,
is why I
ma'am.
was calculating it. Here I had calculated it. Actually, this was the last time I was the TA for this course. So I had calculated it from the graph. using the equation. Right now, I'm trying to calculate it by subtracting, by analytically, to be more precise.
Ma'am, do you have the last year question paper?
No, actually, as I said, that I am affiliated with NPTEL only through this course. I'm affiliated with NPTEL through PMRF program only. I Besides our interactive sessions, I don't have any interaction or knowledge about the exams or even the professor who teaches this course. I
Okay, ma'am.
Okay, average of this. Okay, so minus is just the sign that it is decreasing. This will be your CC, and you can do the same thing for may not have this reading. So you will have 0.05 value of CS. And don't worry about the exam. I don't think it will be very difficult. Okay. And then we have been asked
Ma'am,
to
for scoring pass marks, assignment questions are enough.
Yeah, I think so. I don't think it's going to be that difficult. CS.
But for scoring high, you have to practice like books, many books.
Yeah, for scoring higher, that is so this will be your CS over CC. Okay. On the basis of average, E log sigma dash plot, calculate the void ratio at sigma naught of 1000. So we can interpolate it here. We can use the formula even. We got the CC as 0.2.
Ma'am, CC is the compression index. What is CS?
This is the swelling index at unloading, na? So this is the unloading part of the curve, isn't it? So this is the slope of this. This is CC. Okay.
Yes, ma'am.
So you have delta E of sigma 1 sigma 2. Okay. Is your CC. And then let's take E from here. So sigma 1 will be 800, sigma 2 will be 1000. So E at 1000 will be equal to CC over log of 800 over 1000. This is 0.2. Calculate this. 0.2 log 10 of 8,000. This will actually be change in sigma 800. I should not have taken 800. I should have taken, yeah, 800 is fine. This is the reading that I'm taking. So if I'm taking 800 to 1000 dE, that is 0.61 minus dE 1000. dE 1000 is 0.6 V dE, and your dE comes out to be minus 0.0194. So it will be lesser than 0.61. So E at 1000 will be 0.61 minus 0.0194. This will be 0.59. So you see, it has to be greater than that at 1600, but it has to be lesser than that at 800. So it quite matches. So I think it is fine. E1000. Now we can next question. Soil profile is shown if a uniformly distributed load delta sigma is applied at the ground surface. What is the settlement of the clay layer caused by the primary consolidation if clay is normally consolidated? See, this is a very good question. Okay, so this is your soil strata. This is the ground level, and you have a clay layer at a depth of 6 meters. And when you want to calculate the settlement due to consolidation, due to primary consolidation, we usually do it at the center of the layer. Why we do it at the center of the layer? It's not always that we do at the center of the layer. We are actually calculating the shortest path for the water to escape. So from here, you don't assume, because we're talking about one dimensional consolidation, we don't take water escape in this direction. We take it in this and this direction only. So we are calculating the longest path of water. If excuse me, if the soil was impermeable here, the longest path that the water had to take for escaping this layer was the entire depth of the layer. At that time, we would have taken H as the complete depth of the layer. But since it has sand above and below, that means it is a double drainage, which means that the uh, water here can leave just adjacent to it only. It does not need to transverse the whole of the height of the clay. So the maximum distance that the water will have to move will be basically h by 2 only. That is why we calculate the consolidation at the middle of the layer. Okay. So then
Yes,
what we
ma'am.
do is, this is the loading here, 100 soil profile uniformly distributed applied to the ground surface. Okay, this is not a foundation load. If it was a foundation load, then we would have taken a distribution like this. But because it has been mentioned that this is a load like this, it will simply be transferred like this. Just- Okay. So the second thing it is saying that the soil is normally consolidated. Normally consolidated. Why it is asking that is because when the soil is normally consolidated, you are supposed to take the CC value. And when the soil is over consolidated, then you're supposed to take the CS value. And while loading, if before loading, your, let me say that the pre-consolidation pressure for the soil was 70. I started delta sigma from 0 kPa. So from 0 to 70, the soil will act as OC. But from 70 to 100, it will act as NC. So on this increment of the load, I will have to use CC, while on this increment of the load, I will have to use CS. So here it's already given that the soil is NC. That means that throughout the interval, the soil will have, see, we have been given delta sigma, we have not been given sigma, which means that it does not mean that the soil has no pre-consolidation pressure because we are starting from 0. There is a pre-consolidation pressure. The total will be, if the soil has a pre-consolidation pressure of PC, it means that in absence of this load, the loading on the soil is PC. That is how, as I start loading this soil, it will behave as a NC soil. If this was any lower than PC, then my soil would behave as OC. And if it was any higher than PC, then my PC would itself change. It would change to match the loading that is on this soil. Did you understand what I said?
Yes, ma'am.
Okay. So the clay is normally consolidated. Pre-consolidation pressure is 200 kP. So when I don't apply this delta sigma, this whole thing is under a pressure of 200 kPa. Then I apply delta sigma. Okay. Use CS is equivalent to 1 over 5 Cc. We have not been given Cc. Soil profile. Only distributed load is applied at the ground. What is the settlement of clay caused by primary consolidation if clay is NC? CC has been given as, I had to give Cc as 0.178. Okay, so when the soil is Nc, your settlement will be Cc over 1 plus E H log sigma naught dash plus delta sigma dash over sigma naught. Okay, something. One second. Void ratio is 0.8. Okay. Sigma naught dash we can calculate using this gamma dry 14 into 2 plus gamma sat 18 into 4 plus add 19 into 1.75. But you have to remember that we have to excuse me, we have to take the effective stress. We can't take the total stress that is not in the formula, because we're not talking about the stress that is being carried by the water. We're only talking about the stress that, because if your stress is carried by water, you will not see the deformation. We want the deformation will be when all of the stress is being carried by your soil skeleton. That is when you have to calculate the effective stress. 14 into 2 plus, so you have to subtract 10 into 5.75. Okay. So sigma naught dash at the center we calculate. I think this comes out to be 175.7. Okay. So we got the pressure over the soil, the pressure that is acting without this. This is the load that is acting. Then we have been told that the soil is NC, which means that your pre-consolidation pressure will be equal to 175.75, and your CC, sorry, your SC will be equal to 0.178 over 1 plus 0.8 log into obviously H 3.5 log the base 10 275 175.75. Let me check. 14 into 2 plus 18 into 2 plus 19 into 1.75 minus 10 into 5.75. This is actually 75, 75.7. And here it has to be let's calculate 0.178 into 3.5 over 1 point into log 1.75. This comes out to be 126 mm. Okay. So the next question is, if the pre-consolidation pressure is 200. So here pre-consolidation pressure was 75.7. Now if pre-consolidation pressure is 200, I am loading, initial load is 75.75 kilonewton per meter. This is sigma naught. Sigma naught plus delta sigma is 175.7 kilonewton per meter cube. And this still is OC soil. From here to, from sigma naught to delta sigma, sigma naught plus delta sigma, I will still have an OC soil. So I will have SC is equal to, uh, eh, yes, simply have to divide this by 5. This will be 126 over 5. 25.2 mm. Excuse me. Now the third part is that what if your S sigma naught or pre-consolidation pressure is 150 kPa. So in that case, you are moving from OC stage to an NC stage. So you will divide this into two segments, SC1 and SC2. The SC will be equal to CC times H over 1 plus E naught, starting from 75.75 to 75.75, like 150 minus 75.75, isn't it? So it will basically be up till pre-consolidation pressure over 150 minus 75.75. It comes out to be, basically you are breaking down the whole increment into two parts, plus CS times, actually we have CS here, CC times, this will be 150 minus 75.75 over 175.7. Okay, it's over.
Yes, ma'am.
Can you calculate this?
Yes, ma'am.
So I will just mention that you will get a result of 44.5 mm, most probably. Okay. Okay. For each part, calculate and plot a graph of E versus sigma at the beginning and end consolidation. Okay. So what we have been given, we calculated the delta H, delta H, delta H. This was 126, this was 44, this was 25. So we know delta H over H, this is the change in height. This is equivalent to delta E over 1 plus E. Okay, so change in void ratio will be equal to delta H over H into your initial void ratio. Okay, so case 1 में we had E naught as 0.8, delta H was 126, delta E will be 126 over 3.5 into 1000 into 1.0648 EF E naught minus delta E, which will be 0.73. Similarly, we can calculate for this case and this case. And let me see if I have drawn any graphs for this. Um, yeah, I have a graph for this. Paste it. Okay. So you will see that this was normally consolidated. It had a greater slope. The one that was over consolidated throughout had a lower slope, and one that had both NC and OC branches had kind of intermediate slope. Okay, this was actually this was supposed to be something like this and this. a result this. Okay, this is a kind of intermediate. Normally consolidated clay layer in the field of following values are given. Thickness of clay layer, void ratio, compression index, average pressure on the clay layer, delta secondary compression index, what is the total consolidation settlement of the clay 5 year later after the completion of primary time. Okay, so we know that there are two kinds of consolidation. There is primary consolidation and then there is secondary consolidation. Primary consolidation is only due to the expulsion of the water from the voids and due to the change in the volume of voids. After, see, you have a fixed soil, it will have a fixed volume of voids. Thus, it will have a fixed capability of consolidation. So, after this complete consolidation has taken place, what happens is that sometimes under a um, prolonged period of loading or prolonged period of straining, the soil solids start uh, reorient and they form some kind of settlement which is called the secondary settlement, and it has nothing to do with change in the volume of voids, uh, and it is time dependent.
Okay, ma'am.
Okay. So our consolidation primary consolidation settlement will be 0.28 cc over 1 plus 0.8 plus E naught into 8.5 into log of 2650 970 92650. Okay, then we have secondary consolidation, which is equivalent to C alpha over 1 plus EP. We calculate the final uh, void ratio here. This comes out to be 2.15 inches. Primary consolidation settlement. Then EP delta E is simply 1 plus E delta H over H. Delta E over 1 plus E was delta H. Delta H. Actually, I was not to multiply this. I simply had to do multiply by 2.8. Delta E is 0.038. Thus, E after primary consolidation will be E naught minus delta E, which will be 0.8 minus 0.038, comes out to be 0.762, and your change in void ratio due to secondary settlement is 0.02 over 1 plus 0.762. This comes out to be 0.011. So your final EF will be EP minus delta E secondary consolidation 0.011, 0.762 minus 0.011, 0.751. This will be your final void ratio. Okay, I think that is it for today.
Okay, ma'am.
Okay, thank you very much.